Okay, so with that background, now we're going to analyze this thing. And incidentally, in calculating the slopes, I calculated rise and run between every pair of points, right? So that's all explained on the full MCR video, which goes into a lot of detail. Okay, so I'm going to give away the secret now. The function should be a power function. Okay? Make sense? No, doesn't make sense. I'm just saying it should. I know the physics. I can tell you why it should be a power function. But you don't want to get into the analysis. You don't even know enough trig to start if you take the second semester and learn the trig. If you really want to know, you can, but you might not need the trig.
Why is it?
So you might want to go directly to applied calculus if you're going to the more advanced course. Okay, well, anyhow, function should be a power function. Now, what's the form of a power function?
Y equals kx squared.
That's one power function. Y equals kx squared is a perfectly good and wonderful power function, but it probably isn't going to work for this because that certainly doesn't look like an x squared graph.
Y equals abx.
Well, y equals what?
AB to the x.
ab to the x is in the exponent.
X.
That would be an
Oh, I'm
exponential
smart.
function.
I'm smart.
You're close. So it is, I'll fill, you want to tell me?
Y equals ax
To the B,
Yeah.
B,
Now, usually we use P here.
P.
I
don't know
use
what-
B because HTML with the font that I'm using and with a lot of fonts, the P extends down here so far that it almost looks like a multiplication. Okay? But usually we'd use P here, but B is perfectly okay. That confuses it with exponential. So just to insert this, the exponential function would be y equals a b to the x, because an exponential has a base, b, right? Okay? Okay, so we got y equals ax to the b. Okay, what are we going to do with that now that we have this graph?
Plug in y and x.
Find y's and x's, right? Okay, very good. Everybody understand? That's what we do.
Yes.
So, we don't want to use points that are too close together because there's a lot of relative uncertainty. It's difficult to estimate small distances with a small percent error. The bigger the distance, the less percent error you have in estimating. And we've talked about that, but it's one of those things that's maybe difficult. And we don't use data points. We use points on our curve because our data points tend to have errors. They're too far to the right or left. They're too far up or down. There's always something wrong. Okay? For example, I estimated these data points to the nearest half centimeter. Well, the length is here, right? I estimated the lengths to the nearest half centimeter, so any one of these points could be half a centimeter to the right or left on this scale. Now, there's 10 centimeters. Half a centimeter is pretty small, but it still could affect any given data point. The count could be plus or minus 1, so that would raise or lower data points. So the data points aren't anything but a guide to where you draw your curve. Okay? So I'm just going to make that statement. Data points guide where to sketch the curve. Okay? So, we select points on the curve, not data points. So I'm going to just pick this point and this point. Okay? Somebody tell me what you think the x-coordinate of this point is.
Mm,
20.
no.
It's not 20, 20's here.
I
16
can't.
or 17?
It's between 10 and 20, right?
Did-
15. Okay, let's project it down and, see how that
I've heard
is.
like 16
It's
or
actually pretty close to 20,
Told you.
okay? But I'm guessing 18. Okay?
I think it's.
I said it's clearly not 20 because I'm looking at it from the side. Of course, yeah, looking at it from the front, it's closer to 20 than I thought, so you have bragging rights, but I'm still going to say 18.
Candace is always right. How did we learn that? That's why.
We got a
She
y
messaged me
coordinate.
last night.
I really did.
Y coordinate, here's 60, here's 70, that's 77.
Yes.
Okay? Now the x coordinate here, is that thing, yeah, okay. It looks like 48, and it looks like 41. Okay, so now I've got 2 data points. How many data points do I need for this model?
Just 2.
Why 2?
Because you gotta cross it out. You gotta cross the
You gotta
thing out
find
to
one.
find the other thing.
You gotta cross what out?
The thing to do the other
You're
thing.
thinking of the process rather than the general overview. The reason is, yeah, I mean, what you're thinking is right, but it comes down to how many parameters do you have to evaluate before you have a good power function? Yeah, you gotta know what A is and you gotta know what B is, right? So you gotta have 2 equations that you solve as simultaneous equations, right? Well, you know that you get 1 point from one simultaneous equation from each point, so you need 2 points. If this was a quadratic, you'd need 3 points because you have 3 parameters. Ax squared plus bx plus c, you have A, B, and C. Okay, so we have this, if x is 18, y is 77. If x equals 48, y equals 42. I think that's what I said, but that's what I'm seeing right now, so that's what we're going to work. We understand, we get those from just picking 2 points on the curve and doing a good estimate of their positions, right? Okay? Now, I know what power this thing should be. Okay? I don't know necessarily what A is, although I could figure it out, or what A should be in the ideal case. But I do know what the power function should, what the power should be. We'll see how close we come out. It should be 1/2, 0.5. Just committing myself. Okay? It's not going to come out exactly 0.5, but it should come out pretty close. If it doesn't, then that means I did a bad graph, which is entirely possible. Okay, so now, what are the equations? Could you write down the equations?